All right, guys, we want to start thinking about how to store information because if we're going to perform operations with a computer, we need to store inputs to those operations. We need to store the output of the operation. We need to store the instruction of the operation somewhere. And we are going to store those in some kind of memory. So we need circuits that will preserve a state. And the most simple way to do that is through something called an SR latch, or a set reset latch. And the reason why this circuit is called a latch is because it has a state and it preserves that state as long as there's power to the circuit. And then when you apply a signal to it, momentarily, it can change the state of the circuit. And but that signal doesn't have to be continuous in order to preserve the state. So to give you an example, if we have a light bulb on a simple switch, and the light bulb is off, and I turn the switch on, then the light bulb goes on. If I turn the switch off, then the light bulb goes off. So that circuit has no memory. It's completely dependent on that switch being on or off. It doesn't remember the state of the circuit after I turn the switch off. Well, this circuit's going to be different. The circuit will be in its initial state, either on or off, and then I should be able to apply a signal to it, change the state of it, but that signal is momentary, just an indication, turn on or turn off, and then the circuit will maintain that state. And so that's what we call a latch. It's latching that state into the circuit. The way that we do this, and you can see there's two actually independent circuits here on the board, and it's just easier for me to film it this way, but this circuit here is an SR latch built with 2 transistors. And this circuit here is an SR latch built with a set of NAND gates, okay? Not AND gates. And in both cases, I'll let you guys work the logic out by looking at the circuit yourself. You'll see that the way that they are continuous is on the transistor side. Let's look at the transistor side. You have your collector, your emitter, and then you have your base in the transistor, and you have on that both of these. So you have basically power that cannot cross the transistor without the base being set. But you'll see that in this case, and it's hard for me to see from here, but this base is connected to this collector, and this base here is connected to this collector. So these two, the output of this feeds into the input of this, and the input of this feeds to the output of this, right? So that's how you get that continuous circuit. Okay, and over here it's exactly the same. The first pin here is input, which is to this switch here. The second pin is the second input of the NAND gate, and that is being fed as from the output of this NAND gate to the input here. And then the third pin is the output of the first NAND gate, and it gets fed as input to the second NAND gate. So you can see the same sort of circuitry applied on the integrated circuit as we have on the transistor example. Now these two switches, they're not continuous. If I push them down, they come right back up. So they make their connection, and then they release their connection, they release their signal. In this case, they are connected to ground, so they, in a sense, short the circuit that they're connected to. And so you can think of these lines, from this switch here to this emitter. Sorry, not to the emitter, to the base, and this line here to the base. These just simply short these bases, and this same thing here is basically we're sending a 0 to the base here. We're sending a 0 to the base here. We're sending a 0 as input to these NAND gates. So if now both of these are on, right? And you can see, doesn't matter how many times I push this, they're on, they're in the on state. And if I set a reset signal, I set a high to reset, now they turn off, and when I release that, there's a memory that they are in the off state. When I send a set signal and release it, it stays set. And if I push it again and again and again, it doesn't matter. The only way to reset it is to push the reset. So you have set the bit in memory to 1, and the reset it to 0. So now we can store the state of a single bit, and we have two examples, one with transistors and one with an integrated circuit that does that. So you can see again, this is going to take up quite a bit of space, and this is more compact. And there's many ways to build an SR latch. You can do it with transistors. You can do and then you can do it with gates, which take more transistors. There's more transistors inside of here, and these are NAND gates. You could use NOR gates, and then you can also build more sophisticated latches that have additional features. But these are the basic set reset or SR latches. So this is really what we need to do to just understand how memory works, and now we can go on to use other integrated circuits that have memory. Now, in this case, also worth noting that it's not using gates or transistors is not the only way to build a memory. Modern memory uses capacitors, which are, you can think of like little storage tanks. We haven't really talked too much about capacitors, but you can have a high voltage and a low voltage in a capacitor, and modern memory has many tiny capacitors that they maintain voltages in, and these are just like little wells in silicon, and then the circuitry sets those voltages to or drains them, so it fills those little wells up or drains them. And there's also because these things are so small, they tend to bleed, and there's a whole process for keeping those wells at their present state, so it refreshes them. And this is a modern memory, but we don't need to get into that per se to understand how memory works and how a bit is stored. That this accomplishes that mission. So this is our introduction to that and the introduction to the SR latch.